Hello, everyone. Welcome back. Today, we're going to talk about the standard normal probability distribution. So our goals are to use this distribution to calculate basic probabilities, but also understand, be able to calculate what are known as critical values, which will be useful later on in hypothesis testing. And then we'll show how to use either Microsoft Excel to calculate probabilities from a standard normal probability distribution. Now, first off, let's back up and review a couple ideas. So normal probability distribution or normal distribution is kind of like a bell-shaped curve, like we see here. Well, this is particularly the standard normal probability distribution. And many things tend to follow this in large populations. For example, height tends to follow a normal distribution, or IQ, or other parts, not only physical height, but also like your length of thing. I believe like the length of your arms tend to follow normal distribution, the length of your legs tend to follow normal distribution, and many other things do in life. And so it's a very important distribution to understand. And we'll learn in the future that actually, even when sampling data from what's not a normal probability distribution, that if you have a large enough sample, you can use the techniques we're about to describe to analyze it using it for a normal distribution. Now, a normal probability distribution is also a continuous distribution. So in past videos, you may have talked about discrete probability distributions like a binomial distribution. That's discrete because we talk about with the binomial distribution, we talk about flipping a coin, rolling dice, something like that, where your possible outcomes are only individual numbers, individual possibilities. So that's what makes it what's called a discrete probability distribution. You can only have your answers, your outcomes can only be very specific values. But with a continuous probability distribution, you can have eventually an infinite number of values or anything in between. So for example, think about height, for example, which follows a normal distribution like this, which is a bell-shaped curve. So imagine you can have any possible height you want between certain values. Okay, so you think about being between, like, say, 6 feet, if I'm like a man, for example, who's between, say, 6 feet and 6 feet 4 inches tall, there's an infinite range of possibilities in between those two values. So that's why it's continuous. You can have any one of those values. And so also, in the sense of talking about what's the probability that someone is exactly 6 feet tall isn't very useful, because when I say exactly 6 feet tall, I mean like 6.000, as many zeros you can imagine. And so there's just not that many people who'd be exactly 6 feet tall. But with a continuous distribution like this, it's more meaningful to say how many people are there, or what's the probability, what's the fraction of people between 6 feet, or men between 6 feet tall and 6 foot 4 inches tall. That's a more meaningful question. And so with a continuous distribution like this, we don't talk about the probability of very specific outcomes, individual outcomes. We talk about the probability of between different outcomes, between like a range of outcomes. So now let's talk about what the standard normal probability distribution is. So first off, remember that probability distribution has to follow certain rules. And one of the main rules is that if you sum all your values up, that you have to get a 1. Okay, all your values sum to 1. That's also true of a continuous distribution like this. For example, the standard normal probability distribution like this, its area under the curve, which essentially is a sum of all the values, is 1. That's one of our main characteristics there. Now, the standard normal distribution is a normal distribution with the parameters of mu equals 1. So the mean is 1, right in the middle. Remember, a bell-shaped curve, your mean is right in the middle. And the standard deviation of 1. We get this from the z-score. We call it the z-score. We found a z-score by taking a data value, subtracting the mean from it, and then dividing by the standard deviation. And what that gave you was a distribution essentially in terms of standard deviations. So, for example, that gave you a normal distribution where your mean is right, or your mean, which of course is in the middle, is 0. And then it's the thing of it, each z value then is in terms of standard deviations above the mean. So a z of positive 1 means you're 1 standard deviation above the mean. First, remember, your standard deviation gives you an idea of the amount of spread in the data. If you're -2 standard, if your z-score is -2, it means you're 2 standard deviations below the mean. And a lot of those same characteristics we talk about are also true. So once again, the area of this curve, since the sum of all those values is 1. And then in this form, it's really useful also because any value between And if we say if a value is beyond 2 standard deviations above the mean or 2 standard deviations below the mean, then we say that's an unusual value, and that the probability of something lands between 2 standard deviations above or below the mean, we say that's kind of an unusual event. And so also we can, from this use of the z-score, we can convert any normal distribution into a standard normal probability distribution. So then we're going to use this and actually find probabilities, kind of describe how we do that. So we're going to do this, find the probabilities in a couple different ways. We'll use tables, which is kind of the old-fashioned way of doing it. Then we'll also talk about how you can use Microsoft Excel to also find the same probabilities. So let's look at an example. Let's come over here to the right. And number one, or let me actually start this way. So let's say from a standard, let's abbreviate that, normal distribution, just abbreviate all that. Find the probability, let's abbreviate that, and we'll start number one. Let's say the z-score for z is less than, let me write that better, z is less than negative 1.37. Okay, so first, even though we have this picture over here, let's draw this picture again, a very basic picture. Can I get an idea of what we're talking about? So here's our distribution. Okay, now here, z, and also a couple more things to mention. So since your mean is in the middle, if z is positive, you're always above the mean. Okay, always this side. If z is negative, you're always less than the mean. So z of negative 1.37 is about right here. So once again, here is 0 right in the middle. And then, so let's say it's about right here. Now we're talking about less than that. We're talking about this area here. So once again, with the continuous distributions like this, we talk about areas. So in other words, if this curve, if the area under the curve represents the sum of everything, then what's the probability if you draw, like, imagine these are people, like say this is height or something like that, it represents height. And then what's the probability that someone has a height that's less than 1.37 standard deviations below the mean, for example, and we'll, in future applications, we'll see something like this. That, what's the probability of getting, drawing someone from this part of it right here? Okay. I also think the same question is, what fraction of this whole distribution is this little area right here? You think of it both ways. So let's find that. Okay. So what we're going to do is want to find the probability. We'll write it this way, that z is less than negative 1.37. Now, you can also write z is less than or equal to as well, because effectively that's the same thing, because the probability that you're any one exact value is basically 0. Now, how we're going to do that here is we're actually going to first use a table. And I'll also put this table in our notes at the end of the lecture. So let's do that. Actually, I'm going to move it over here. Okay, so this is an example of a z table. Let's explain what it is first. This is a standard normal cumulative probability table. And what it gives us is, you see this picture right here. So this is a normal distribution, the standard normal distribution. There's a z right there. So what this, on this table, it gives you, what it gives you, and the entire table gives you values to the left of z. Okay, now on this side, see, these are all negative. So what that means is that these are all values below the mean of 0. Okay, so for each number, and this is all rounded off to 2 decimal places, usually, like for example, this one right here is this one starts, and their value is less than this, but this table only goes this far. For example, negative 3.40 up to negative 3.49. Okay, it gives you those individual values for the areas under that curve to the left of z. Okay, and then on this side, then, since these are all positive, this gives you the areas of the values for the z-scores that are above the mean. Okay, so let's show to this first one. Okay, so what the table gives you is the table gives the area under the curve to the right of your z-score. Okay, so let's find it for this one. So let's find negative 1.37. So it's negative, so we're in the right section. It's below the mean of 0. So go to negative 1.3 right here. Okay, then we go over to where it meets 1.07, so negative 1.37, okay, is going to be right here, and that value is 0.0853. So the probability that z is less than negative 1.37 is equal to, once again, that value, let's go find it again. So go down to 1.3 first, and go over to where it meets 0.07. If you add those together, that would be negative 1.37. And that's going to be point, where those two columns, row and column intersect, is 0.0853. Okay. Now, once again, it gives you both the area under the curve, but the area under the curve is also the same as the probability. This is also the same as a fraction of the total population, whatever this population is. In this case, the z-scores that are less than 1.37. Okay. And so as a percent, then this is, and this is not exact, but it's approximate. So 8.53%. Okay. That's that probability. Now, let's do another one, our next one. Then we'll show how we can do the same thing using Microsoft Excel. So let's just do number 2 down here. Number 2 is, the first one said find the probability that z is less than 1.37. Find the probability that z is greater than 3.32. Okay. Now, so let's look at that. Let's draw a picture of this. So remember, here is 0. Now 3.32 is bigger than 0, of course, so it's going to be to the right of 0. And it's actually going to be way over here. So I should back up just a bit so you can see this better. So it's going to be kind of over here, pretty far over here. And now this time says greater than, so we want the area to the left of this. Okay. Now, if you notice, once again, our tables in both cases, our tables only give the value to the right of this. Okay. So maybe wondering how we're going to find this. Well, what the table does is, what we can do then is actually use our rules of probability to help us find this. So basically use the idea of complements. And so this is the complement of, so the left, what's the left of this is the complement of what's to the right. Okay. So what we can say then is the probability that z is greater than 3.32 is the same as 1 minus the probability that z is less than 3.32. Okay. So what the table gives us are values to the right. So if we take, remember the area under the entire curve is 1. So if we subtract this area, the unfilled in area, from 1, that's going to give us this little bit that's left over. And so if we do that, then we find that from the table. So from our table, let's find this value for 3.32. Okay, so once again, we're on the positive side, all our z-scores are positive. Let's come over here, so 3.3. Okay, if you notice, now this one starts with zeros. This is 1, 2, 3, and so forth. So 3 point, maybe hard to get all, we can't get all in here. So 3.32 is go down to the row for 3.3, go across to intersect with the one with 0.02, and that's going to be 0.9995. So from the table, probability that z is less than 3.32 is equal to 0.9995. So the probability that z is greater than 3.32 is 1 minus that. 1 minus point, not 1, but 0.9995, and that's going to be 0.0005, so very small. Okay, and as percent, that's actually going to be 0.05%, so a really small value. And as we learned in the past, that is beyond 2 standard deviations above the mean, and so that would be considered kind of a rare event, an unlikely event. And you see by the probability, think of unlikely event as probably being less than 5%. That's quite a bit less than 5%. That's a lot less than 1%. So that would be a very unlikely event. Okay, so that's the idea. So from these tables, we can find the probability of, either a value to the right, which comes straight from the table, a value to the left of a z-score, which is basically what we do is just 1 minus the probability that 1 minus the probability from the table, which is to the right. And now let's take a look at our next example. We'll start right here. So the probability that z is between 1.00 and negative 1.00. Okay, so once again, let's draw this as a picture. Here's our standard normal distribution. Here's 0. So here is 1.00 right here, and here is negative 1.00. So I want to find this area right here, area between those two. Now, obviously, the table is not going to give us that right away. So I have to think about how we can do this. So remember what the table gives us is always the area to the right. We can still use that to our advantage. We think about it a little creatively. So what this is going to be in terms of areas is the table will give me the area to the right of 1. It'll also give me the area to the right of negative 1. And so if I subtract this little area right here from everything less than 1, I'll get that. So this is going to be, so you can put it in terms of areas, kind of show a picture in terms of areas. So this is going to be, if here's 1 minus, once again, I know my picture is not the best, but that's okay. Subtract that. Okay, so look at this again. So what I said is if I take from the table, find the area that's less than 1, that fraction that's less than 1, subtract from it a fraction that's less than negative 1, once you get both these values from the table, that's going to give me what's in between. That's what we're going to do. Okay, so then we can write this as the probability that z is between negative 1 and positive 1 as the probability that z is less than 1 minus the probability that z is less than negative 1. And once again, we get both these values from our tables. Let's find those. Okay, so probability that z is less than 1. So 1 is positive, it's above the mean of 0. So it's going to be on this side. And so once again, we just have to find 1.00. Okay, so go down to 1. And then 1.00 is this value right here. And that is 0.8413. Minus from that. So now we go to the other side of the table, since it's negative, go to the negative side and look for negative 1.00. And right, so here's negative 1.00 is right here, is this 0.1587. And let's just calculate that, use your calculator. And so 0.8413 minus 0.1587. And that's going to be by this 0.6826, or about or approximately 68.26%. Now, you might recall a discussion about let's actually read the table just a moment. A discussion about the normal distribution and mentioning that between one standard deviation above and below the mean, you have approximately 68% of the values, and that's exactly what this shows. Okay, so between -1 and 1 standard deviations from the mean, you have approximately 68.6 amount of all your data values. This is also true, for example, height. So height of men or women have approximately 68% of all people within 1 standard deviation above or below the mean. Okay, now what I'm going to do now, then let's talk about how we can actually do these same things with Microsoft Excel. Let's go back over here. In fact, I'm going to go back. Let's see if I can go back in each one. I have enough space to do that in each one. This one almost, let's see. So what I'm going to do is let's go back and do each one with Microsoft Excel and see how this works. So I do this Excel, count the probabilities from a normal standard deviation. We have this command we put in. So norm.s.dist, and the S there is there because this is the standard normal distribution. And notice the two things we put in are Z, the Z-score, and where it says cumulative. In this case, we choose true for cumulative, so just put in the word true. Okay, because we want the cumulative distribution. That means basic cumulative is everything, the sum of everything up to that point, and that's exactly what we've been doing with the table. Okay, so this gives us exactly the same value with the table, except in some cases we can actually do things we can't do with the table. For example, if you want to find values in between, to a higher level of accuracy, we can do that. So for number 1, the probability that Z was less than -1.37. So what we're going to do is we're going to type into our Excel. We'll go ahead and write what the commands look like. So norm.s.dist for the normal standard distribution. We're going to put in -1.37 and then true, TRUE. Okay, let's do that. So I have an Excel open right here. So remember, to calculate things, put an equal sign first. Now, if you start to type it, you'll get several options. Now, don't pick this one. This is actually for a regular normal distribution, not a standard normal distribution. So we go to norm.s.dist, double click on that. Once again, it shows you in the Z and the cumulative. So for Z, we put -1.37 and then true, because we do want the cumulative distribution. And see, the value it gives us is 0.085343. 0.085343. Okay, if you look, that's actually a little more accurate than what we're given in the table. The table only given to 2 to 4 decimal places. This now usually gives us to 5. Okay, 0.853, actually, well, 6 places actually, 0.853. This is 0.85343. Okay, but basically it's the same thing. All right, so for number 2, we have the probability that Z was greater than 3.32. Okay, now we can also do the same thing. This is going to be equal to, so what we're going to do then is in Excel, we can also do this as 1 minus this. So 1 minus norm.s.dist, and then 3.32, and then true. Because once again, this is going to give us, as we did with the table, the area to the right of this, and then, or sorry, the area to the left of this, and then we're 1 minus that to find the area to the right. Let's do that. Let's go down here, so equals 1 minus, and then go to norm.s.dist. So 3.32 for our Z-score. Then once again, true. We want the cumulative distribution. And that's going to be in this case, a little more accurate, 0.00045. Okay. Okay. Actually, didn't mean to do that. There we go. All right, and then number 3, for the area in between, so the probability that z is between -1 and 1, then as you might guess, we just do as we did with the table. So norm.s.dist 1.00 true, then minus the same thing with -1. Okay. And let's do that. Let's see what we get. Let's move down a bit so we have plenty of space. So this is equal to, just type in, start to type it in and make sure you don't go backwards. So this is 1, and we just put 1, so this is 1.11. And then true. Then minus, I'm going to start type it in. Let's make sure we get the right one. So norm.s.dist, then -1, and once again true. Yeah, and so this gives a little more accuracy. So 0.682689. So the same thing. Okay. And so we can use Microsoft Excel as well. So it's kind of good to be able to understand how to use both in case you need to use either one. Okay. Now, next, and let me take a moment, make sure I have enough space. So let me, give me just a moment. I should, but I just want to make sure, yeah, there should be more than enough. I just want to make sure they have enough space so I don't have to have problems having to copy and paste anything later. Okay, so now what we want to do is actually want to, in this case, find the z-score for the given probability. Okay, so I want to find the z-score for the given probability. All right. So number 1 for probability of 0.2. So what this means, we're basically going backwards, what we just did. So let's draw a picture again. And let's actually move back up here so we can see our distribution. So once again, for our distribution, okay, let's draw a picture. So this time we know the probability, we want to find the z-score. So once again, here in the middle. So right in the middle is 0.5, okay? So if you have a z-score of 0, your probability of 0.5 is basically half of your data, half your population is below, half is above. So it's probably 0.2, that means it's going to be to the left of this. So what this is going to mean is that 0.2 is, say, maybe about right here. Let's say this area under the curve is 0.2. And what that means, this over here then is 0.8 on this side. I want to find what that z is. So this is going backwards. Okay, so we'll show you can do the table, and we'll also show how we can use Excel as well. Okay. So look at the table. In the table, find the probability closest to 0.2. Probably won't be exact, but one the closest to 0.2, then use that z-score. Okay, so we're going to use that z-score when you find it. So the probabilities are the 4-digit values, okay? The ones of 4 decimal places. So we're going to find the one of that that's closest to 0.2. It won't be exact, but it should be the one that's closest. That we'll just use that then. And then we'll find the z-score that goes with that. Okay, and remember, once again, since if it's exactly 0, it'll be 0.5. So know we're on the left side of 0.5. So it's going to be in this part of the table. We're below the mean. So we just have to look through here to find 0.2. For example, here, this is 0.02 something. So we need to go higher. And the closer we get to 0 is going to go higher. This is too far, it's 0.3. So find, okay, here we go. So 0.2, um, yeah, so 0.211, these are going down, 0.202, 2005, 1.1997. So if we look right here, this should be the closest one. The closest one is 0.2005. Okay, both these are further away. So the closest one is 0.2005. And the Z for that value, let's take a look. So let's find it again. 0.2005, the Z-score for that is -8, and then the rho, and then 0.04, so it's -8, -0.84. So once again, then that rho is -0.8 rho, and then it's 0.04, so the Z is -0.84. Okay, so from that, then we can go backwards, and for no probability, we can find the Z-score that goes with that. And sometimes that is really useful to understand. Some of the questions you may have is you may say, well, you want, maybe you want 90% of people, for example, if you're designing let's say a seat for an airplane, for example, okay, people who design. So obviously from the standpoint of the airlines, the airplane itself, you'd like to have as many seats as possible. You have more paying customers. Of course, there's also concern for the amount of weight in an airplane, but also for comfort. If you're going to be on a 7 or 8 hour flight, you don't want to sit in a really tiny seat. So they may design, for example, try to have a seat that will fit, comfortably, say 90% of the people. So what you have to do then is figure out, then kind of going backwards of this, figure out maybe what Z-scores correspond to give you that 90% value. Then you have to then find out what heights go to those Z-scores. So that's an example of how you might use this in real life. Let's do one more of these. Then we'll show how we can do this on Excel. In fact, let's go ahead and do that. So let's actually go back to here. It was actually say in Excel how to do this. All right. So to define the Z-score for a given probability, we'll do this. So in Excel, this is going to be norm.s.inv, since inv is essentially like inverse, going backwards. Then the probability, we're going to use 0.2. Okay, let's go to Excel again, do that. Let's just put a little space so it's easier to read. So once again, type in NORM and look at your options, and it's right here. Okay, NORM.s, because once you're using standard normal distribution. Okay, click on that, and then type 0.2, and as you see, it gives the same thing, but with more accuracy. So -0.84162. Okay, so that's the Z-score that goes with that. We can also say, if you want to write this kind of the way you did the other probabilities, we can say the probability that Z is less than negative a point, I'll just use 0.84, is basically 0.2. Okay, let's do another one of those. Now this we're going to state a little bit differently this time. So number 2 is going to do it down here. Let's say I want to find the 90th percentile. And we'll see that's the same thing as finding the probabilities is less than 0.9. Okay, so the 90th percentile, remember what that means is that 90% of all values are essentially at or below this value. And by low, we mean less than. So think about this on a picture. Once again, this picture of this normal distribution. Okay, think about where that would be. Here's 0. Well, if 90% of the values are at or below this value, so this is going to be somewhere over here, okay? And so this then is going to be 90% or 0.9, and this little area right here, this will be 0.1. And so once again, we're looking for this z value right here, which is the cutoff for that. Okay, so find the z value such that 90% of the values are below this. Okay, if those, that's the same exact same question as finding z or a probability of 0.9. Okay, the same thing as asking, find the z. So if you pick a value to the right of this, any random value to the right of this, there's 90% probability of picking a value in this area, this interval. Okay, it's the same question. So we do exactly the same thing. Okay, now, once again, let's do it both ways in the table. So in the table, the closest value to 0.9 is, let's go back and find that. Let's go back to the table. Okay, now since this time we're on 0.9 is above 0.5, we're on the other side of the table. So this is the values are less than 0.5 or less than 0. Go to this side and find the value that's closest to 0.9. Also, you won't find 0.9 on the other side anyway. Let's look. So here's some 9s. So go back to find 0.9. We have to go pretty far back here. Okay. So yeah, we're zoomed in. So 0.898, 0.8997, 0.9015 is actually the closest one is right here at 0.8997. So the closest one is 0.8997. It's only different by 0.003. And look at the z-score that goes with that. So come over here to the row. This is the 1.2 row, and then the column is 0.8. So then that says the z-score is equal to 1.28. Okay, that's a cutoff that gives you the 90th percentile. Okay. So 90% of the values are less than that, and then 10% are greater than that. Okay. Now in Excel, this is going to be once again, so norm.s.inv for the inverse, and then we just type in 0.9, and this will give us a even more accurate answer. Let's go back to Excel. Okay, so do a similar thing. So equals, just type in norm, go down to .s.inv, and then type 0.9. And yeah, as we said, it's a 1.281552. Okay, so that is the 90th percentile. So 90% of the values are below that, 10% are above. And also in terms of probability, if you pick any data value at random out of this population, then there's a 90% chance you're going to have a z-score. Will have a z-score less than 1.28 and 10% chance of z-score greater than. Okay, so that's the idea. So that's essentially doing the same thing going backwards. Now, our last topic we want to talk about is something called a critical value, which will be more useful to actually look at hypothesis testing in the future. Let's talk about critical values. And then we'll just start a new page. Explain what they are and how to find them. We'll see it's very familiar to what we've been doing. Okay. So it says a critical value. Let me just read this. For a normal distribution, a critical value is a z-score that is used to separate abnormally high or low values. For example, z equals negative 1.96 is a useful critical value because 97.5% of the area under that curve is to the right of that value. Okay. Similarly, a z of 1.96 is a useful critical value because 2.5% of the area under that curve is to the left of that value. Okay. And now if you notice why this is important is basically we're separating the basically 95% that's in the center and then 2.5% to the left or right. So let's kind of draw this picture, kind of explain what they're showing. Okay, so here is 0. Here is 1.96, and over here, this should be symmetric, is negative 1.96. Okay, and so between these two, you have 95% of your values are 0.95. And this little area right here is the lowest 2.5%. Now let's do it in percents instead. This is 95% between those z-scores. This is the lowest 2.5% here and the highest 2.5% here. Okay, that's what it's saying. Now, so what these values are, these are in terms of critical values, we're calling critical values, is therefore it says 95% of the area is on the curve is between these two values. So the expression, we're going to use what's called z of alpha. It denotes the z-score with the fraction alpha to the right. So this is kind of backwards, or the other way of doing with the table. So this is to the right. So for example, the z here, and we'll also do this in terms of fractions. So this value is going to be z of 0.025, 225% or 2.5% is to the right, okay, of this. And this critical value is going to be z of 0.975 or 97.75 is to the right of this, okay? Once again, what this says is 2.5% to the right. And then here is this 97.5% to the right. Okay, that's just the way it's defined. Because as we'll see later on, we talk about finding like confidence intervals or hypothesis testing, basically using this information to make conclusions, make inferences about larger populations. You want to know essentially what are the small value to the right of that, what are the chances of being as a separator of how unlikely some event of being wrong is, essentially. So this just way is critical value defined is basically area to the right, and then this little value right here as this decimal gives the area to the right of that. Okay, so let's do a couple of these. So here I'll just say finds number 1 z of 0.1. Okay, so what does that mean? Is that so 10% of the area is to the right of this z-score. So I want to find this z, okay? All right, and so let's draw a picture again to help us out. And this we'll see, this is just like we did just finished doing, finding the probabilities, okay? Except we're thinking of it in terms of the right to the instead of the left. So here's 0. Now 10% to the right, that's going to be way over here. And this is going to be 0.1% here, then 0.9 or 90% here. Okay, we're trying to find out what z this is. Okay, that separates essentially the top 10% and the bottom 90%. And if you notice, this is kind of like what we just did. Okay, we just found the 90th percentile. Okay, so that's exactly what this is showing. The same thing we just did in the previous example. Okay, we're finding the value that separates the top 10%. Okay, because how this is going to come into play and actually will happen in the future is we're looking for, in doing kind of hypothesis testing, or basically trying to test whether some conclusion is correct. What you want to do is you want that to be essentially be an unusual value. You want your chances of being wrong to be really small. So basically, we want to figure out a z-score. So if we get a certain value, and basically if it's want to be an unlikely value, unlikely to happen by chance, I want to show there's actually a cause and effect. So you want to show that the chance, the probably something happened by chance is really small, maybe way over here. This would be your separator, and then determine whether to conclude that it didn't happen by chance or it could have. Now, I'll just say, so from previous question for this one, then this z was 1.28. Okay, so this is the critical value. So actually I should back up. So more precisely, this is critical value 0.1 is 1.2. This is your critical value. So it's called a critical value because it separates the bottom 90% from the top 10%. We use that in testing. Okay, now let's do one more of those. It's number 2. Let's do Z.99. Okay. Once again, what this says is want to find the Z score. I'll say in which 99% of particularly the area under the curve is to the right. Okay, so 95% of the area of the curve is to the right. So let's once again draw this. So always draw a picture that will help you to make sure you understand what it is you're talking about. Okay, I'm sorry to go and do a better job than that. No, it's not a whole lot better. We get the idea. So here is 0. Now, 95% to the right, what that means, we're over here somewhere. And basically on this side, we have 0.99, 99%. And this little section right here is only 1%. Okay, so I want to find this Z. Okay. Now, what we can do then, we can also use the table or Excel. Let's just use Excel here. And so what we're going to use is the same one we just used a minute ago to find essentially the inverse. Okay. Use Excel to find Z so that 0.01 is to the left. Remember, that's what the function is going to give you is 0.01 to the left. Okay. Although we want to find, which is finding the same thing. And this is the value where we have 99% to the right of this, but what the Excel also the table gives you is what's to the left. So we want to find we're 1% to the left. And so we're going to, let's see, let me write this better. And so this is going to be then this inverse. So norm.s.inv and then 0.01. Okay, let's do that. Equals, just type in NOR, and then right here, norm.s.inv, and then 0.01. Make sure you do this. If you did 0.99, that's going to give you the place where 99% to the left, and that's not what you want. 0.1 is going to be negative 2.32635. Okay. Or to 2 decimal places, approximately 2.33. Okay. So for this critical value, Z of 0.99 is negative 2.33 approximately. So this is our critical value. So in some tests, that might be the value you need to make. Essentially, a critical value is called critical because the value we use to make a decision about whether or not to accept or reject the results of our test. Okay, so let's review what we've done today. So what we found is we introduced the idea of a continuous probability distribution, how it's different from a discrete probability distribution. Simply, we talked about the standard normal probability distribution, as in we can convert any regular normal distribution into this by using the z-score. Then we saw how we can use this to calculate probabilities and how a table and also Excel gives us the values to the left of any z value. And then we also found how we can find, so we can find the probability to the left of a z value, or if you know the probability, how we find the z value that goes with that. Then also be able to find the critical value, which tells us is a cutoff between our particular area to the right of that value, which is the same concept as finding the probability, the same concept as knowing the probability to the right, as the left rather than finding that z as well. Thank you. Have a good day.